number of slides to present on what we would see as being the key power management features required for the ideal ultra-low power energy harvesting next generation smart sensor node. So so this is based on some data we presented back at NRHarv 2018. But basically, amazingly useful systems can be designed to operate on surprisingly low average power levels. So on the right-hand side, I've just put in a few data points on this. I suppose we know of a commercial ocular retina implant system for the eye, and it's targeted to work on a power level of 250 nanowatts and would require a wireless charge once per month. Or a Bluetooth radio system on chip, and that will transmit 4 bytes of data per second for 1 hour a day and draw an average power of 2.4 microwatts. So this energy gap on the lower right-hand side, at one stage we were talking about were there enough ambient energies to power a useful system, and we've absolutely passed that barrier whereby for many applications, energy harvesting could totally replace that primary barrier. Regarding storage devices as well, the solid state on-die lithium-ion based electrochemical cell research group in Tyndall tell me they're targeting 15 microwatt hours of energy storage on just 1.5 millimeters by 1.5 millimeters of die. So to conclude, there are sufficient ambient energies to be harvested for many systems, which will greatly extend battery lifetime to ideally match the full system lifetime. We're thinking now 25 plus systems, or possibly go energy harvesting only. If you consider in many applications, such as we'll say sensing concrete stresses in concrete in a bridge, it would literally be thousands and thousands of euro, tens of thousands of euro to replace a battery. So for that reason, that's the thing. So here we have quite a busy slide, and what I've gone into a little bit of detail here is in showing the typical power requirements, power components in an energy harvesting smart sensing node, as we would say on the edge of IoT, or consider a smart wearable device. So around the left-hand side of the drawing there, I'm showing 4 harvesters. I'm showing photovoltaic, thermoelectric, vibrational energy harvester, RF energy harvester, in conjunction with a primary battery which may be used for real-time clock or initial boot. And the ULP PMIC then, which is the subject of the PMIC in this talk on the left-hand side, that ideally manages the power transduction and processing at highest efficiency from the variable pulsing, low voltages, high voltages, DC or AC voltages, voltage or current source in nature. And that's over to the right-hand side. There's generally something like a multiple output voltage point of load PMIC, which will have a collection of buck regulators or linear regulators to create the well-regulated voltages for the system functions. Consider on the left, then in the energy harvesting section, we'll also have many other features to be implemented, such as impedance matching with the sources. We'll have possibly current monitoring into the storage devices, current control, condition monitoring of the load or switch of or storage devices, gas gauge functionality, and indeed load or storage device switch out dynamically by the system to prevent leakages. Further downstream then, I talked about the buck regulators here. There may be things like low noise LDOs to power analog front ends or the data converters in systems. Around this system, there might be an overall control function, which might do something such as switch out power supply switching during intervals of sensitive radio transmissions. I suppose another thing to note is in general, we're talking about average power levels of microwatts from the left-hand side of this system. And over on the right-hand side, your core, your I/O, your various types of memories in the system. These guys are going to call, we'll say, instantaneously in the typical system on chip, between 1 and 10 microwatts, sorry, 1 and 10 watts over the 10 to 100 nanosecond region time frame. So you're looking at microwatts on average, going to be able to provide very rapid, instantaneous power levels, often up towards the 10 watts, as various peripherals within the system on chip light up. So we'll move on then. So I've taken that whole left-hand energy harvesting and ultra-low power PMIC system, the storage devices, and I've said, you know, ideally we want to integrate all of these guys into the everlasting energy source, the infinite life battery, which is totally green. And I think nearly all of us in the world would subscribe to the goal of powering our systems with this energy sourcing package. Possibly in some limited applications, it may become an energy source on chip. I guess the battery companies might be the only ones who would argue with that ambition. So we move on then. So our solution then for the full ideal ultra low power PMIC platform is going to be flexible, configurable, ultimately programmable, and will enable the derivative PMIC ASIC to be spot on for a given application, but it'll consider the full system. I suppose to power an application in its perfect environment. That could be to ideally tune that will be the thing. If we look then down into some of the detail about the requirements of the solution, a single switch mode conversion cycle will have a period often of less than about 100 nanoseconds. And the system or load being powered may be something like for a few minutes every day, as little as that. So you're looking at getting to a 10 to 6 fold dynamic range in time and consequent power transfer. If you look at something like photovoltaic, people talk about a 10 to the 4, 10 to the 5 dynamic range in the energies to be harvested. And then if we look at the useful energies, the voltage from TEG, thermoelectric devices, we might get useful energies from the 30 millivolts, all the way up to a number of volts for a PV stack. We'll say electric devices, piezoelectric devices, maybe in the 50 to 100 volts, all the way to triboelectric devices, maybe many hundreds of volts. So we're looking for a wide voltage range on the input, wide voltage range on the output. Typical storage elements are 3 to 4 volts. System bias voltages begin we'll say less than 1.8 volts. So we're looking for ideally 0 to 5 volts in on our first PMIC, well, 0 to hundreds of volts when we put in some high voltage switches, maybe 1 to 5 volts out. In that, the platform should be buck boost, and we want to implement current control, voltage control, and that will enable power control, impedance control, or energy control on any input or output if we consider implementing digital control algorithms. We want to cold start with the lowest power or voltage. And here I've shown the platform we're developing with respect to just a range of, it was a survey we did a couple of years ago, a range of commercial parts on the marketplace. We said, okay, our focus will be to go digital, our focus will be configurable, flexible, the platform philosophy, and we want to go useful power sub a microwatt. 2-3 years ago when we went into this program, commercial parts entered at about 10 microwatts. They're all extending down, and we want some decent efficiency. So here's our platform, and I guess I've talked a fair bit about this platform now, but basically we taped out our version 1 PMIC platform, which is a block array in April of this year, and we implemented a 4-switch quasi-resonant power path for 4-switch quasi-resonant buck boost. Power path, inverters, gate driver sections, modulators, should do over 95% efficiency from 1 microwatt up to a few hundred milliwatts if you consider higher voltage. The platform is all based on having independently triggerable subsystems. So for all of the functionality, asynchronously triggerable. So for instance, we would have dynamic band gap and hysteretic sampling control resonant hysteretic sampler digitally settable up system, which would come to life within 3 microseconds. A range of 100 nanosecond dynamic comparators. I've shown there ultra low energy on the hysteretic controller. And again, we're trying to do digital to time converters based on oscillators ranging 0.2 of a hertz all the way up to tens of megahertz. And we're getting down into the 4 nanowatt type systems. We have an ultra low energy ADC system in development. On this platform, we've implemented a variety of cold start systems. I'll talk about them in a minute. Process choice was very important to us, and we've chosen a process which was designed for industrial, medical, and automotive. And you can design component system blocks on it over the temperature range -40 to 175 C. So then, if we look at some cold start solutions, it's a particular area for the enables research from Tyndall into this enables ecosystem. But if we look at a typical, just one of many commercial PMICs, we have shown a part here based around a Meissner oscillator, 1:1 coupled inductor. And this is a large discrete coupled inductor for the systems we're considering, 6 millimeters by 6 millimeters by 3.5 millimeters. But it achieves cold start from 20 millivolts. So as part of the enables research in Tyndall, one of the things we are looking at is, can we disappear this very large discrete magnetic, which is hundreds of times larger than the power management silicon required, and can we disappear this inductor onto the silicon in the first instance? So we have fabricated in the Tyndall lab here, coupled inductor. It's a 1:11 thin film magnetics on silicon based inductor. And we've also designed and taped out some circuitry around this, and that achieves cold start. I think it's from something like 80 millivolts. And yes, because it switches at such a high switching frequency, about 17 megahertz, it is drawing about 6 or 7 milliamps. So it's getting there. As we disappear the magnetic, it is a tough challenge because magnetizing inductances reduce, and therefore magnetizing currents all increase. And the other thing happens is oscillating circuit currents increase as well. Because of the reduced magnetizing inductances, circuit oscillation frequencies increase to give you increased oscillation circuit currents. So it's a very, very tough challenge to disappear the magnetic. But to go further on this, we're now implementing PCB embedded 1:50 and 1:100 cold start transformers, which can be disappeared into the substrate in under the PMIC. These guys should come at an intermediate space between the discrete solution and the thin film on silicon, because inside the substrate or the PCB, you can put more inductance. And for all of these, for these two new technologies, the embedded coupled inductor in substrate, packaged substrate or PCB, or the thin film on silicon, we are also developing volume supply chains. We are putting as much focus in onto that activity, so that they're not just research technologies. Well, they are advanced research technologies, but we are ensuring that there will be supply chain for them. So if we look at another little bit of detail in the cold start blocks, one of the things we have taped out on this platform is what we believe is going to be the lowest power cold start block of all the commercial parts we've surveyed. In that, we believe this will cold start and create a bias voltage from 0.5 microwatt. Thermoelectric devices are going monolithic, so there are often, one class of thermoelectric device is multiple series connected PN junctions. So they don't really require very low voltage for startup. So we believe low power cold start will be important. Traditional on silicon circuit for cold start is showing there. And if you take something like 180 nanometer CMOS, an on-chip inverter-based ring oscillator, and Dixon charge pump stage, will start typically with 350 millivolt devices on CMOS. And this scales with the CMOS technology. So a separate part of the research we're doing as contribution to the Enables program in Tyndall is we're looking at low voltage cold start, and without transformer. My previous slide were two types of coupled inductor or magnetic device-based cold start. But here we've taken standard 180 nanometer CMOS, and based on setting up a ring oscillator with stages comprising off-state leaking latches operating in sub-threshold mode to another off-state, and a ring of those, we have reduced the intrinsic startup for 180 nanometer series CMOS from about 350 millivolts, the typical, down to 150 millivolts. This, we believe, as well, is extremely low power in that this gain stage, one stage of this at a 2:1 gain stage, operates from only 5 nanoamps. So an incredibly low power cold start, transformer-less, and it's on silicon only. So that's another piece of the research. Here, just if I can briefly show, you may recall Peter a few moments ago mentioned the Enables transnational access. He talked about free access into the Enables ecosystem. And this is an example of a program, an application which has just been approved. And Dr. Navneet Swan in Ulster University, Jordanstown, came to Tyndall saying, I have some excellent technology in triboelectric generators. He's shown a generator here. Small difficulty, he says, in that my triboelectric devices generate bipolar pulses of up to 600 or 700 volts. But this technology promises very, very high power density. So he came to Tyndall, and we said, okay, as a transnational access program, let's see what we can do for you in terms of designing a discrete power management solution, or let's see what could ultimately happen if we were to use the 200 volt superjunction MOSFET devices, which are available on our chosen process. And could we create a 10 IC interface block with the idea that if your research in triboelectric devices becomes very commercially viable, that at the same time we might ultimately have a PMIC which is dedicated to it. And you know what? We can possibly adapt our buck boost technology. And I show here from one of my colleagues on this call, it's from a paper from 2014 from Aldo Romano, showing a synchronous electric charge extraction circuit, whereby the electric charge extraction is synchronous with the mechanical vibration from a piezo device. This is the kind of thing we can alternatively do on our flexible programmable buck boost platform. And we're going to look at, well, what if on our buck boost platform we were to put in the 200 volt superjunction devices which are available on the platform, and what kind of power processing efficiency and how much energy would we get for Dr. Navneet Swan's device. So that's an example of, now that's a large feasibility study that's planned to take 30 days, which would be the upper end of it. So in conclusion, we're about the concept of introducing advanced digital control, flexibility and features to the energy harvesting ultra low power smart system node to either design out the battery or extend it to match the system lifetime. Into the Enables ecosystem then, we're putting the Tyndall hardware in terms of the whole atoms to systems ecosystem, bringing expertises across thermoelectric device, crystal design, all the way through piezo MEMS, electromagnetic transducing MEMS devices, or integrated magnetics technologies, advanced data converter research in MCCI and RF circuitry, the solid state electrochemical cell development group, There's a wearable medical systems group, biophotonics group, ICT for energy efficiency, smart agri. So bringing those groups, bringing those expertises in conjunction with our ultra-low power PMIC design and trying to offer it within the Enables ecosystem and within the context of the full program and partners offerings. So that's it from me. Hopefully I didn't run over too much.
Thanks, Seamus. That was great, very interesting. So we could move on because, yeah, we're going a little bit over time. Could we move on to Peter, please?
Yes, of course. I will share my screen again. So, Seamus, you have to stop sharing.
Let me get my stop. Sorry, Peter.
No problem. So do you see my presentation mode now?
Yes.
No, but this is not presentation mode. It's only on preview.
Okay. Next trial. Can you see now the presentation mode?
Yes.
Yes,
okay.
Perfect full screen, that's fine.
Okay, thanks a lot. So as we have now the key power management IC features seen from Seamus, I now go a step further in our outline. I now will talk about the power converters for DC sources, including maximum power point tracking. So as you all know, a major challenge in micro energy management for energy harvesting devices is to adjust the voltage from the harvester to a storage or to a load so that we can supply an electronic load. Typical harvesters provide a voltage which is typically depending on the used harvesting technology. For example, if you use thermal gradient, solar, or vibration, it is also depending on the ambient energy source. And due to that reasons, you somewhere end up in some voltage ranges like a couple of millivolts, but also if you're using other technologies like piezo harvesters, you could really get some several tens of volts. On the other hand, the application devices like sensors or wireless radios need a constant supply voltage in the range of 2 to 4 volts. So in general, there are two types of voltage regulators available. The one is the linear regulator, the alternative is the switching regulator. The linear regulator uses a control deviation of its own output from a reference voltage and controls the transistor. So a constant output voltage can be generated from a variable higher input voltage. Since the control element, which is here a transistor, works in the linear operation mode, this type of converter produces high losses, and these losses depend on the current flowing through the regulator, and they also depend on the voltage difference. So to reduce these losses, the voltage drop over the regulator has to be reduced, and this results in the so-called low dropout regulator. Another option for a DC power regulator is the switching regulator. This switching regulator uses the transistor only as a switching element, which is either completely on or completely off. Sorry. It has much lower power losses, and these power losses are not depending on the voltage difference between the input and output. These voltage losses or power losses mainly occur to the losses in the inductor. These are ohmic losses and due to the switching action. For a switching regulator, you can also implement an up conversion of the voltage. So you can use lower input voltage and use the switching regulator as a boost converter, as an up converter. This only depends on the combination of the main functional element, which is the inductor, the capacitor, and the diode. A big obstacle in energy harvesting is to cope with very small voltages, for example, produced by solar cells at low illumination or from thermoelectric generators at low thermal gradients. For this purpose, I already mentioned you can use a so-called boost regulator. One possible architecture for such a boost converter uses a JFET, which is a transistor that is normally on without any control voltage. Normally on without any control voltage. This transistor, as you can see it here, forms a conducting path together with the inductor here, L1, which is one part of a coupled transformer. The second inductor L2, which is coupled to the inductor L1 in reverse polarization, charges a capacitor, which you can see here, C1, to a negative voltage. As soon as this negative voltage of this capacitor C1 reaches the negative threshold voltage of the JFET, this JFET stops conducting and all the energy in the inductor L1 is pushed into the diode towards the output. And this way, a much higher output voltage can be generated from a lower input voltage. In this way and in this architecture, you can see here a self-oscillating structure is formed, which has a startup voltage which is much lower than the typical threshold voltage of a transistor. This circuit, for example, can start with voltages as low as 20 millivolts, depending on the turns ratio of these coupled inductors L1 and L2. After the startup phase, so as soon as this circuit is running, the MOS transistor T2 is taking over the switching action, since this MOS transistor has a much lower on resistance than the JFET here, and so we can improve the efficiency. The typical efficiency of this circuit is depending on the input voltage. You can see that here from the diagram, and it typically ranges between 40 to 60%. So in energy harvesting, we're dealing with smallest power sources. So it's mandatory to extract the maximum power possible from such sources. Therefore, the maximum power transfer theorem has to be considered. This theorem states that the maximum power from a load can be extracted when the voltage resistance, when the load resistance matches the source resistance, as you can see it here, or when the source voltage on the load is half of the open circuit voltage of the source. So maximum power point tracking means that the converter, which is directly after the harvester, always draws the maximum power possible from this source. This can be done, for example, by adapting the duty cycle, so the switching cycle of this converter. It results in a variation of the input resistance of this voltage converter, and so we achieve a matching of the input resistance of that voltage converter and the source resistance of that source, which might be an energy harvesting element like a thermoelectrical harvester. An algorithm which does such a maximum power point tracking is called perturb and observe. In this algorithm, the duty cycle of the power converter is changed in a certain direction, which you can see here on the diagram, and the current or the power output of the power converter is investigated. If the power output is increasing, then the direction of the change is kept, so we would potentially end up at that maximum here. If the power output is decreasing, then we would like to change the direction of the change, and we also end up here at that maximum. So in this block diagram, you can now see a boost converter with a digital maximum power point tracking. This converter employs a JFET to implement an ultra-low startup voltage, as shown in one of the previous slides. In a programmable mixed signal IC of the company Silego, a maximum power point tracking loop is programmed. And this loop is using the perturb and observe algorithms. The power output is measured with the help of the output current, considering that the output voltage to be constant since we're charging a battery. In the Lego IC, the function of amplification, filtering, differentiation, and signature determination are carried out. The block diagram shows the whole architecture, including the TEG, which you can see here. The picture displays a practical implementation on a printed circuit board with the different ICs, the output capacitor for filtering, and the transformer. The current consumption of this maximum power point tracking is 80 microamps at 1.8 volts. But here it has to be considered that the maximum power point tracking is activated only for very short time frames, and though you're reducing the mean power consumption significantly. Finally, on this chart, you can see the measurement results of the boost converter with the maximum power point tracking. In channel 1, in yellow, it's shown the constant battery voltage, VBAT. Channel 2, in blue, is the current in the battery. Channel 3, in purple, shows the open circuit voltage of the TEG, which is generated by a lab power supply. In channel 4, in green, is the output voltage of the source, so the voltage under the load VTG. So this voltage under load VTG is half of the open circuit voltage from channel 3 in purple. So this shows that the boost converter is working in the maximum power point according to the maximum power point theorem due to its maximum power point tracking loop shown in the previous slide. Okay, this was my last slide on that topic. Now I'd like to hand over to Aldo.
Let me share my screen. Okay, I hope you can see my screen correctly. Okay, in this section, I will try to review the main types of power conversion circuits for vibrational piezoelectric transducers and try to describe some possible solutions to the problem. So, piezoelectric transducers are quite popular for extracting power from vibrations. They're normally made with layers of piezoelectric materials, some structural and elastic layers, and electrodes. In many cases, a seismic mass is added to increase the harvested power and tune the resonant frequency. So when a piezoelectric material undergoes a deformation, some displacement in the centers of symmetry of the fixed positive and negative charges in the crystal produces an internal electric field. And as a result, electric charge is then induced on the electrodes, which can be collected to harvest energy. So in a simplified view, the behavior of a piezoelectric transducer can be modeled as a current source IP, depending on vibrations, with a parallel capacitor CP, mainly due to the electrodes. And in order to develop a power converter, we will need several blocks. We will need an interface whose task is to extract the maximum possible charge from the transducer and store it locally in DC form in a storage capacitor, which is the second element required for the architecture. And finally, we will need a power management unit with the duty of providing a suitable supply to our external load, or keeping it disconnected in case there is no sufficient power. Now I will try to go through several solutions for implementing either the interface or the power management unit. So the interface circuit can be easily implemented with passive components. For example, a common solution is the full bridge rectifier. It's quite effective. However, the main drawbacks are a voltage drop of 2 VD, 2 diodes voltage drops, and a non-conductive region for low voltages. And the conduction angle is also limited because the rectifier starts conducting only when the transducer voltage equals the output voltage, and then turns off when we reach the peak of elongation of the transducer. And the transferred power then depends, on the ratio of input and output voltage. So we will definitely need an MPPT mechanism. Okay. A voltage doubler is a similar circuit which allows to reach a higher voltage of 2 times Vp minus 1 voltage, direct voltage. And third, an interesting solution is the so-called negative voltage converter, or NVC, which is a bridge of cross-coupled MOSFETs. The interesting property is that it provides a zero voltage drop between input and output. However, it conducts bidirectionally when it is enabled. So we will still need an additional single output diode. And several improvements can be implemented with active circuits. For example, the full bridge rectifier can be integrated with an inductor and a switch. The purpose of the switch is to form a resonance circuit with the transducer in order to flip its voltage in the exact moment the rectifier turns off. As we can see in the figure, the rectifier stops conducting exactly when the current generated by the transducer is 0 and is going to become negative at this point. Okay, exactly at this point, we flip the voltage on the transducers and we bring it exactly on the opposite boundary of conduction. As a result, this circuit, this rectifier, has a very large conduction angle. It is conductive for most of the time. Of course, losses may limit the efficiency of flipping voltage and of transferring power. Even in this case, the efficiency and the transferred power depend on the input and output voltages. So even in this case, we will need an MPPT mechanism for optimizing the power. Another interface is the so-called synchronous electric charge extraction, which requires an inductor and a few switches and control circuits. The transducer in this scheme is normally disconnected. And as we can see in the figure, charge is transferred on the voltage peaks of the oscillation of the transducer. When we detect a peak in phase 1, we transfer power from the transducer into the inductor, and then when the transducer has no charge, we transfer the energy from the inductor to the output voltage in phase 2. Okay. And in first approximation, the transferred power is almost independent on the load condition. So this scheme is particularly suited for operating with irregular vibrations. And now, once we've chosen one of the above interfaces, we still need the power management unit to supply the load. The load normally requires a valid supply, ranging from a VDD min to VDD max. The first solution that I propose makes use of CMOS analog switches and voltage detectors, which are a type of commercially available components that can enable or disable their output depending on the absolute value of the input voltage. For example, they are normally used with microcontrollers in order to provide the reset signals in case of undervoltages. There is also some hysteresis which can be extended with external resistors. The component is quite flexible and can be used also in these cases. As we can see, we can configure the voltage detector in order to enable the analog switch when we reach VDD max, and we can disconnect the load when the voltage drops below VDD min. The same circuit can be implemented also with discrete MOSFETs and resistors, and can yield an intrinsic consumption as low as a few hundred nanoamps or less. In this case, it is advisable to use resistances larger than 1 megaohm in order to reduce the static current. In this case, the circuit switches when the input voltage scaled by this resistive divider exceeds the threshold voltage of this transistor. Of course, some hysteresis is also added with the resistor RF. The switching threshold then depends on RH, RL, RF, and the threshold voltage of the transistor. The load is connected and disconnected based on the threshold we decide. Okay. So as Peter has shown previously, we can also use other components. For example, we can use an LDO when the load requires a stable constant voltage. In the previous case, the load will see a variable supply voltage. In this case, the input voltage must be higher than target VDD, and as Peter mentioned before, losses are proportional to the voltage difference between input and output. The LDO also has some constant intrinsic consumption. Okay, so you may want to consider components known as voltage references in case you have very low currents, because they offer better performance of consumption. Okay, and they also need additional capacitance for stability. Then when we connect the LDO, we will see some large inrush current to lower this capacitor. Second alternative is to use switch mode DC-DC converter. The circuit has typically a very high efficiency and operates in a wide range of input voltages, not necessarily higher than the desired output. However, we will need typically an external inductor, and it is also suggested to place, in this case, the analog switch between the DC-DC and the load, so that invalid VDD are never applied to the load during the transient. And another advantage is that DC-DC converters typically also provide additional monitoring signal, typically power good signals, which may be used to directly control, for example, the switch that connects the load. And finally, in the presentation, I would also like to show some possible solutions for harvesting power from multiple piezoelectric transducers, which may be useful in case of irregular and broadband vibrations. For example, every transducer may be tuned to resonate at a different frequency in order to match the input vibrations spectrum. The first solution is passive and involves the use of passive rectifiers, for example, the one shown previously. This configuration is very simple and easy to set up. However, the power extracted from every single transducer depends on the transducer voltage and on the output voltage. So it is quite difficult to have all transducers operating efficiently at the same time, in case the conditions are different. For example, a transducer with high voltage may prevent the other rectifiers from conducting when the output voltage is sufficiently charged. Then the second solution can overcome this problem and involves the use of synchronous electric charge extraction in a multi-source configuration. This can be done by adding multiple input branches to the buck boost architecture. And in this case, the single inductor is time multiplexed between all sources. The charge is extracted individually from every single transducer at every individual voltage peak. Okay. In this case, the great advantage is that the powers extracted from every transducer are generally larger than with passive interfaces, and most of all are independent from each other. However, this solution requires some control circuits that can still, in any case, be implemented with micro power consumption in any case. Okay, I have now concluded my overview, so I will give back the stage to Nicolas to present the next speaker. Let me stop sharing.
Okay, thanks, Aldo.
Yeah. Okay.
So after Aldo has talked about the piezo harvesting technology and the related power converters, I will say a few words regarding energy storage control and monitoring. So energy harvesting typically provides only small amounts of energy from the environment. Therefore, we need some kind of energy storage devices like capacitors or batteries to collect these small amounts of energy for delivering higher bursts of power in short time frames. These storage devices typically need some kind of charge protection or at least charge control circuitry. Here, the aforementioned linear regulator can generate a constant charge voltage from a variable harvester voltage. If we analyze the theoretical equations for this regulator type, it can be seen from that first equation for V out that the output voltage is only depending on the ratio of these two transistors and on the reference voltage, and it's not depending on the input voltage. So for a certain operating point, we can at least generate a constant voltage from a varying input voltage. For storing higher amounts of energy, employing lithium-type batteries can be beneficial. For these devices, we need a control of the charge voltage, but we also have to control the charge current and even the temperature to avoid a damaging of the battery and also to be able to use the maximum storage capacity. Therefore, a voltage regulator with an additional current and even a temperature regulation loop is employed, as you can see it here on that block diagram, which can even be controlled by a microcontroller to add some more flexibility. In some applications of energy harvesting, a state of charge monitoring of this storage device may be helpful, and it could even improve the system performance. Such SOC monitoring will be used, for example, to control certain actions of the application device, for example, when sufficient energy is available. SOC estimation usually employs current integration, which is realized by monitoring the charge and the discharge current and using the difference as a measure of the remaining capacity in the battery. For small batteries and especially for energy harvesting application, such a column counting method is way too power consuming because you have to actively, permanently power your microcontroller. On the other hand, since the open cell voltage of a battery is a rough indicator of the SOC, as you can see it here in the diagram, a simple SOC estimation can make use of voltage monitoring. A simple and power-efficient circuit can compare the battery voltage with predefined values, as you can see it here in the block diagram, and give a rough indication of the battery capacity in form of several steps, as you can see it here in the diagram. This whole circuit consumes less than 1 microamp and is therefore very much suitable for energy harvesting application. So then, for the next part, I'd like to pass over to Aldo again to talk about the performance trends of PMIC.
Thank you. Let me share again my presentation, which you should hopefully start viewing right now. Okay. In this section, I will try to comment about the performance trends of PMICs compatible with energy harvesting applications. And until now, the main hurdle towards achieving successful applications of energy harvesting has been the extremely low available power, often not compatible with traditional power converter modules. However, the awareness of the need of designing an energy autonomous system as a whole has been progressively increasing, and so did the availability of parts with lower intrinsic consumptions. The minimum input power of a PMIC is a very important feature which determines the feasibility of an application in a power-constrained scenario. So in this context, I've tried to collect data from the most effective PMIC available commercially and also from scientific literature. For both categories, I've plotted the lowest value of minimum input power reported every year. The analysis is not comprehensive, of course, but still shows some directions. It can be observed, for example, that commercial PMICs have a clear reduction trend. And in the last decade, we experienced a significant reduction of approximately 10 times recent power converters can operate with input power down to 1 microwatt or slightly less. On the other side, scientific research has also pushed this limit significantly lower, and many PMICs were reported with operation with tens of nanoamps or even less. Okay, a continuation of this trend would of course be very good news for developers of energy harvesting applications. Okay, and I have also a second graph. This graph aims at combining another useful information, which is the minimum input voltage. Sorry. For operation of the PMIC. It is worth to note that commercial products close to the 1 microwatt boundary can also operate with input voltages lower than 1 volt. So these trends are very promising. However, even if lower values were achieved, in order for designs to be successful, the availability of external parts with ultra low power consumption will be still necessary, like sensors, microcontrollers, analog blocks, etc. However, the good news is that an increasing number of these type of components is slowly becoming available. So once again, this is good news for developing energy harvesting applications. Okay, this section is over.
Thank you, Aldo. Then I take over for the last part of the webinar. So finally, I like to introduce 2 use case examples of energy harvesting IoT devices where these technologies which we introduced today are being used. So a first promising field of energy harvesting power supplies are industrial sensors in condition monitoring applications. In these applications, we have sensors which measures, for example, the temperature, humidity, vibrations, or even gases. Here was an estimation of the condition of a machine, of an engine, or even a plant is possible, and required maintenance or upcoming downtime can be predicted. In such scenarios, of course, thermal gradients or vibrations are often available, which we can use to power these wireless radios and sensors. The blue tag of the Fraunhofer IIS is a wireless sensor module, which can be powered by thermal gradients with the help of an integrated TEG and with the boost converter, which I presented here in this webinar. This blue tag is a 36 cubic centimeter housing, and it needs a 3 Kelvin thermal gradient to generate around 150 microwatts of electrical power. This power is sufficient to supply different sensors, for example, temperature sensors or acceleration sensors, and it is also sufficient to power a Bluetooth low energy module to transmit all the data once every second. Alternatively, vibrations can be used with the Viva, which is a wireless sensor module that employs piezoelectric discs to cover its own power consumption. Here we need a vibration level of 0.1 G at a frequency of, for example, 60 Hertz, and this is sufficient to generate 1 milliwatt of electrical power to power the acceleration sensor and the Bluetooth low energy module, which is integrated in that black housing. Another promising application field for self-powered radio systems are tracking systems. These tracking systems are used to locate expensive goods. They are locating containers, assets, or even vehicles which carry them. These tracking systems typically measure the position, and they also employ additional sensors like temperature sensors, shock sensors, humidity sensors. And these systems provide the information to the owner over a cellular communication, and that can be done worldwide. Of course, you can imagine The bottleneck in such tracking applications is the power supply, since such containers or assets are on the road for weeks, months, or even years. On the other hand, vibrations and light are always available in such moving objects. Sometimes even thermal gradients to be used for recharging the battery on the tracking device on the move are available. So here I'd like to introduce our Entras tracking system, which has an integrated energy harvesting interface. This Entras system has all the necessary functional blocks like a GPS receiver, a UMTS communication module, a microcontroller, and different sensors. It provides an additional power supply module with different micro power management function, which we have introduced in that webinar. For example, the different DC-DC or AC-DC converters, and also maximum power point tracking loop. This energy harvesting or power supply module can accept power from solar cells, from thermal generators, and from vibration harvesters. And it even does an SOC estimation of the storage device, which might be in that case a lithium-ion battery. So the power consumption in these tracking systems are strongly dependent on the activity of the system, like position measurement or transmitting the information. So the table on this slide shows the mean power consumption of our tracking system Entras as a function of positions and transmissions done per day. In the last column, you see the area of a solar cell which would be required to cover this power consumption, considering even that the consumption during night has to be harvested during day and stored in the additional lithium battery. On this picture, you see different Entras prototypes in a field test on railway trains to record the present vibration. Actually, this was an enabled transnational project with a partner from Austria. And these measurement vibrations are then used later in the lab to characterize different commercial available vibration harvester. The results of this characterization you can see on the diagram on the right-hand side. In this diagram, the output power of different commercial available harvester as a function of the velocity is shown. So you can see, depending on the performance on the tracking system, for example, position measurements or transmissions per day, this Entras tracking system can be powered completely by energy harvesting, and so you can achieve an unlimited operation time without any maintenance effort. With this last slide, I'd like to finalize this webinar. I hope you enjoyed the presentations from me and my two colleagues. And now I hand over to Nicholas for chairing the question and answer section. Thank you very much.
Thanks, Peter. That was very good. I would like to thank, first of all, the three speakers. I think it was a very interesting presentation. So I know we're going a little bit over time, a bit concerned that probably people who have other meetings and so on. So what I suggest is we just move straight away into the questions and answers, and go. Let's start. If I share in there, we have received a few questions in advance when people register. So if you don't mind, I have them there on the screen. So if any of the three speakers could answer, some of them might not be generic, but so you could maybe answer individually or do a generic answer to all of them, that could be great.
Okay, perhaps I'd like to start with the first question: is what wireless standard or specification are we referring to? I just like to repeat some facts of my presentation. So we are presently using a lot Bluetooth transmission systems, mainly Bluetooth low energy, of course, because it has a very low power consumption, and we have a lot of application where the really a distance, a coverage is not very important. It's often sufficient to transmit the data just a couple of meters. We also have applications, for example, our Entras tracking systems. Here we actually using a UMTS model to really achieve a cellular communication, which is working worldwide. So it always depends on the application and on the distance or the coverage or the range over which you have to send your data.
Thanks, Peter. So if we don't have any more comments about this, I propose to go to maybe live questions. So if you wouldn't mind submitting them using the chat in Zoom, so in that way I can then pass them to the speakers.
Yes, Nicholas, while people write the question, I may briefly comment on question number 4.
Yeah, please. Yeah.
So what kind of MEMS surveillance technology is needed for scavenging low wideband frequency vibration? In these cases, as far as I know, one solution is to stick external seismic masses onto the MEMS so that it basically reduces its vibration frequency. Or another solution is to use the first external vibration to trigger a resonance and a secondary oscillation in the transducers, the so-called frequency up conversion. So there is still the possibility of using MEMS for this type of application.
Very good. One other thing again, while we're waiting for questions, we know none has come yet. Another thing I would like to remind people is this is a part of a series of webinars that enables this organizing regularly. So there'll probably be one sometime in July, maybe August. So please keep an eye on, follow us on Twitter or follow us on LinkedIn, check with our website, and as soon as we have a date and a subject for the webinar, it will be there. So yeah, I'm starting to get here. I have a question here, similar to integrated magnetics to achieve call startup. What level of feasibility can we expect for these integrated inductors for DC converters? That's probably mostly for Seamus.
So I suppose we are conducting a lot of research on this because we believe it will become commercially feasible in, you know, over the next, we don't quite have an idea over the next few years. But if we look at papers published by, if we look at some of the large pure play foundries, largest in the world is TSMC, you'll see a company, they have made presentations since 2016 now saying they're going to introduce power inductor material on silicon. Tyndall is working with some of the other large pure play foundries in the world, some of the foundries from the top three to also commercialize the thin film. And I do also know then that there are a number of substrate manufacturing companies who are doing advanced PCBs by additive processes. And they are also qualifying volume manufacturing processes. They're in the advanced stages of qualifying volume manufacturing processes to use that technology. So what's the difficulty? The difficulty is as you go very small in magnetic size, your magnetizing inductances decrease, your oscillation frequencies increase, and your magnetizing currents increase. So it's tough to get the low currents. But we believe we can get down to maybe 5 or 6 milliamps at the moment with these magnetics. Yes, we can get to low voltage, 20, 30 millivolts, no problem. Large discrete inductors, people are doing circuits around 2 milliamps. Our first design used around 6 milliamps with the integrated inductor. So, but we're going to get there.
Thanks, Seamus. We have another question here from Tian Lan from Gary. He's asking from a practical point of view, obviously, all the technologies were probably getting very close and so on, but for a practical application is what is the cost expected for this power management solution, or even the cost of the whole system, the energy harvester plus the energy management part. So could any of the three, or the three, please, if you could give me your view on this?
Yes, I think that, for example, for the trend of power management circuits, it's a typical trend of silicon components. So we expect the same cost of power converters today. So the trend is positive. For the transducer, the cost may be higher because volumes are typically lower. Materials can be some kind of exotic sometimes. So it depends also on technology. For example, solar cells are now in miniature quite cheap. They're very low cost. Piezo transducers can be produced in volumes at probably lower prices than the past. So I expect as the volume increase, also cost for the most popular transducers should scale down. But until now, the trend is positive in this case.
Yeah, thanks.
Yeah, the power management circuits tend to be nearly always on 180 nanometer CMOS, and that's a relatively, it's a mature node. It's a large geometry node, and lots of companies have it on at least 8-inch wafers. It's very low cost per square millimeter. So it's all about, the cost is all about recovering design cost for the power management piece, for the power management silicon. So, if you have the high volume, exciting application niche, it's worth considering the integrations, where you can get into the volumes that justify custom silicon design. We expect the integrated magnetics we expect those technologies to come out on 12-inch wafers. So again, that piece will be low cost. Yes, the MEMS for the harvesting technologies, that is possibly the toughest part from a cost perspective. But again, people are looking at solid state storage devices also. So it's the applications which will go high volume. They're worth considering these technologies.
Nicholas, it's my case here. Do you mind if I just add a comment to that? So just for the benefit of the audience. Yeah, I'm the coordinator of the Enables project, and thanks very much to the presenters. Excellent presentations. One thing that I would like to point out to the audience is that one should consider the life cycle costs associated with the energy harvesting solution. That it's not so much the cost of the device, it's the amount of cost you're saving by avoiding the need to replace a battery. So for example, many of the people who replace batteries will tell you that the cost of replacing a battery is probably of the order of 60 or 70 euros per maintenance event, whether you're trying to do it in a dry container or a building energy management or a hotel or a hospital. So if you can avert replacing the battery, your energy harvesting device might only cost a couple of euros, but if you avert 3 or 4 maintenance schedules, you can save hundreds of euros over the life of a device by inserting the energy harvesting solution. And this is one thing that we are trying to get information from our ecosystem, trying to understand the actual life cycle cost benefits associated with installing an energy harvesting solution, and for that to be taken into account when people are making decisions about embedding energy harvesting solutions into wireless IoT devices.
Yep, that's very interesting, Mike. Yeah, this is something you forget sometimes. It's not just the individual cost; it's what you are replacing it with. So now that's a very interesting insight. Yeah. I don't have any other comments online at the moment. So what I would suggest is we'll finish the webinar now, and what we can do, if anyone has any questions for the speakers, you all have my email address. Please email them to me, and we'll try to answer them online. For people interested, the webinar has been recorded, so it'll be available to download probably from tomorrow on from the Enables website. If anyone missed the beginning or the end, or there's any comments, or if you know someone who could benefit from watching it, and please stay in touch. If you are a member of Enables, great. You'll be knowing any news, any updates. If you are not a member, we'll encourage you, please go to our site and join us, so you'll get updates of what's happening, what's the next webinar, or any other news on the powering the Internet of Things. So thanks again to the 3 speakers. I think it was a very, very interesting topic. I learned quite a lot myself. So thanks again, and thanks to all the attendees. Okay, take care.
Thanks, Roland.
Bye-bye. Thank you.
Thank you.
Thank you.